Good morning, everybody, including Lydia this time, and welcome back to Galois Theory.
Hi, Lydia.
Emily Rose says hi. Plan for today. Actually, you know what? Let's give Lydia some homework too. But you probably can't even see that. Plan for today. We're going to continue our discussion on irreducibility and talking more about the relationship between a polynomial being irreducible over various polynomial rings. I've got my usual office hours, this afternoon 1 to 2, tomorrow morning 11, and Monday at 11 and 1. Don't forget you have a homework due today. Yes, I know I don't have homework 2 done yet. I've actually started grading it yesterday, but I didn't quite get finished, so I'll get back to you. Just so FYI, homework 4 is going to appear at some point between this class and next class, and it'll be due Tuesday, not of next week, but the following week is the plan.
Except for me, apparently.
Except for Emily Rose and Parker and possibly Lydia. Why would you write in that color chalk on the board?
You know why? What did I do? I'm the one who records your video lectures.
I don't know.
You were part
I tell you what, you all can enjoy your weekend, no homework, relax, do work other stuff for other classes, etc.
Trust me, I need it. I'm still signing up for REU. I gotta have that time.
Oh yeah, you should get that done soon.
Yeah, I know.
Any questions or comments before we get started for today? What'd be a pirate's favorite letter?
R.
Nar, it'd be the C.
What if you just asked what's a pirate's favorite set or something like that?
What'd be a pirate's favorite set?
R, a real number.
Arr! No, it'd be the C again. I thought we just going over this. Okay, someone did ask me in office hours yesterday about when's the exam for this class. Plan is like middle of March, probably week after spring break, and it'll be a take-home exam.
Yeah.
So basically, picture like a bigger homework.
Do we get
That's a little more comprehensive. Do you get partners? Do you want a partner?
Yes. It's more fun with partners.
I'll let you have a partner. And you can work with a partner, and I'll make more announcements on that once we get closer to the actual exam. Like it?
Could we possibly,
No.
could you possibly?
No. Let's talk about. Sorry, was it?
Could you possibly get it before spring break so we could have all of spring break to procrastinate and not actually do it? What?
No,
Yes.
please no.
I think only for Lincoln though.
Who wants to do it over spring break?
We'll see. And also probably not. No.
Well, I get that, but
Fair enough.
I'll announce it like a couple weeks at a time once we get close to what I want to get to, which is I want to get through some field extension theory for the midterm, which is like chapter 3 of the book. FYI, we're getting close to the end of chapter 2 right now. If you're following along,
there's a book.
there's a book. Yeah, it's in the syllabus.
I know there's a book.
I've been taking like homework questions from it even, somewhat.
What is that? You don't have one.
Well, that's your problem. Okay, so last time we spent some time at the end of class looking at some examples of quadratics, and we were able to kind of come up with this hierarchy where if you have some polynomial that is in the integers, yes, Lincoln, because it does actually have to be in each of the sets for this to apply. Being irreducible over the complex numbers implies irreducible over the reals, which implies irreducible over the rationals, which implies irreducible over the integers. And we also mentioned, we didn't prove this, but we mentioned that a polynomial being irreducible over the complex numbers is the same as being linear. And that's just fundamental theorem of algebra. And so what I want to do today is I would like to prove 2 things. I'd like to prove that if you have a polynomial that's irreducible over the reals, then it has to be either linear or quadratic. So this is kind of the first thing I want to prove. Second thing I want to prove is that if it's irreducible, that being irreducible over the integers is actually equivalent to being irreducible over the rationals. Or a polynomial less Lincoln that is already assumed to be an integer polynomial. And that kind of will give us some nice relationships here so that next week we're ready to start looking at specific tests that we can use for determining if specific polynomials turn out to be irreducible or not. Questions, comments before we get going? All right, so let's start off with this one. So we're going to prove that all polynomials, all irreducible polynomials over the reals must be linear or quadratic. So here's the scoop. We're going to start off with the polynomial. We're going to show how do you factor any non-constant polynomial over the reals has to factor into linear terms over the complex numbers. So we're just going to see what relationship do all the complex roots of a real polynomial have to share with each other. So like for instance, x squared plus 1, that's irreducible over r, but over the complex numbers, we would factor it like that. Question, Jonah. What relationship do the complex roots of x squared plus 1 have with each other?
They're conjugates.
They're complex conjugates of each other. We're going to show that happens in more generality, where if you have a real polynomial with a complex root, it's going to have the complex conjugate of that root as a second root. Oh, hi. You can go down. So let's get started. So we're going to start by just taking some arbitrary polynomial. F of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 a1x plus a naught be some real polynomial. We're going to assume that the degree of f of x, I shouldn't say we assume, I should say we know that the degree of f of x has to be at least 1. Why is that?
Because otherwise it's a unit.
Yeah, because otherwise it's a unit or
0.
0, and neither of those count as irreducible elements. Else f of x can't be irreducible. Sorry, what's that?
We assumed that because we are assuming that it's irreducible.
Yes, yeah. Let's let f of x, we're not going to assume f of x is irreducible quite yet. That comes later. Basically what we're going to do is we'll factor it over the complex numbers and say, now suppose that this is irreducible over the reals, and then what can we say about all these complex factors?
Exciting.
So let's suppose that we have some root. And I'll follow the book's example on this. We'll call it gamma, which is going to be some complex number that's not a real number. So c minus r just means something that's in the set of complex numbers, but not in the set of real numbers. And suppose that is a root of f of x, meaning f of gamma is equal to 0. And what we're going to do is we're going to show that if you take the complex conjugate of gamma, you also get 0. So, quick question. If I were to give you something like 2 plus 3i, what does it mean to take the complex conjugate of that, Harper?
It means that you would make the imaginary component negative.
Yeah, keep the same complex number, but you just replace the imaginary part with its negative. So the complex conjugate of 2 plus 3i would be 2 minus 3i. Complex conjugate of negative 7i would become positive 7i. The complex conjugate of 6 pi would be
6 pi.
6 pi. Thank you for answering that while I was trying to figure out who I wanted to ask, etc. So if it's a real number, to begin with, taking the complex conjugate doesn't do anything. Technically, you're going from like 6 pi plus 0i to 6 pi minus 0i. That's the same thing. But if it's something with a non-zero imaginary component, you're taking the negative of its imaginary component, but leaving the real part alone. So I claim that f of complex conjugate of gamma would also have to be 0. So why is that? Then the complex conjugate of f of gamma would be equal to the complex conjugate of 0. Jackson, what's complex conjugate of 0?
0.
Correct answer is 0 minus 0i, but yes.
Oh, wait, but what if it was already 0 minus 0i, then wouldn't it become 0 plus 0i?
No, but it was 0 plus 0i, because clearly 0 equals 0 plus 0i. What? I don't understand what's so difficult about that. So what does that mean? Let's actually write out what it means to take the complex conjugate of f of gamma. So what that means is we're going to get that 0 is equal to f of gamma bar, which is a sub n gamma to the n plus dot 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 plus a sub 1 gamma plus a naught bar over all of that.
We're not actually asserting any of these roots exist. We're just saying if there is one.
If there happens to be one.
Okay.
Yeah, like if f of x is something like, I don't know, x squared minus 4, where all the roots are real, then this is a vacuously true statement. So, all right, Lincoln, because I know you've had complex analysis. What nice property does the complex conjugate have with respect to addition?
It's what property do you call that? You call that being a homomorphism. Oh, okay.
C to C.
Well, okay. The complex conjugate of A plus the complex conjugate of B is equal to the complex conjugate of A plus B.
Yep. Turns out here's a nice property of complex conjugates. They break up nicely over sums.
It's a linear operator.
That's a linear operator. They also break up nicely over products. It's not too hard to prove that. You all can prove that in your off time. Which means we can split this up into complex conjugate of a sub n times the complex conjugate of gamma raised to the nth power plus complex conjugate of a sub 1 complex conjugate of gamma plus complex conjugate of a naught. Technically here, we're also saying something like complex conjugate of a to the n is equal to complex conjugate of a raised to the n. But this is just a consequence of that one.
At least whenever.
When n is a natural number, which it is here because we're looking at polynomials. All right, Jonah, riddle me this. what do we know about the complex conjugate of all of our coefficients? So what relationship, for instance, does complex conjugate of a sub n have to a sub n?
It's the same as a sub n itself because they're all real.
Yeah, exactly. We know that since this polynomial is a real polynomial, these are all real numbers, which means if you take their complex conjugate, nothing happens. So this just turns into a sub n times gamma to the n, complex conjugate of gamma raised to the n plus plus a sub 1 times gamma conjugate plus a naught. And this is, I'll mention over here to the side, since each h sub I is an element of the reals. But what's this expression? This looks an awful lot like this formula, but with x replaced with gamma bar. That's just f of gamma bar. So in other words, gamma bar must also be a root. Of f of x. So in other words, if gamma is a root of your if gamma is a complex root of your polynomial, the complex conjugate of gamma will necessarily also always be a root. Notice that this is something that's only true for real polynomials. Like you could always have a complex polynomial, something like f of x equals x minus I, where something like I would be a root, but its conjugate negative I would not. But what we did just prove is that if you happen to have a polynomial whose coefficients are all real, whenever you have one complex number, like if 1 plus I is a root of your real polynomial, 1 minus I must necessarily also be a root for that real polynomial. Was that? It's not one of those fake polynomials. Exactly. So, with that in mind, let's do some factoring. I'm just going to keep this first line up here just so we have that formula, it doesn't get erased. So then, by the fundamental theorem of algebra, the old FTA, we know over the complex polynomials, we can factor f of x into linear terms. I've already said f of x is non-constant, so it has to have at least one linear factor. Hence, you can factor entirely into linear terms. So what I'm going to do is I'm going to throw an a sub n out in front, and then just list out a bunch of all the other linear factors over the complex numbers of our polynomial. And because the order of our factors doesn't matter, we're going to put all the factors corresponding to real roots first. So write this as a sub n times x minus beta 1, x minus beta sub k, times x minus gamma sub 1, x minus gamma sub 1 bar, x minus gamma sub s, x minus gamma sub s bar. So what are we doing? So the idea would be we're doing something like factoring x to the 4th minus 16 into linear terms, which over the complex numbers we know we can do. Sorry, Lydia, I don't know if you can see this. Factor x to the 4th minus 16, I have confidence that you know how to do that.
I can't see it. No.
I have confidence Lydia knows how.
Am I able to adjust the camera? Is that possible?
It is, but don't.
Be careful.
So, for those of you who are here, how do you factor x to the fourth divided?
I don't know, you could always give me permission to change that angle of the camera.
So this is just kind of an example off to the side of what we're doing here. Let's say we have x to the fourth minus 16. Isabel, how can we factor that?
First, x squared plus 4 times x squared minus 4.
X squared plus 4 times x squared minus 4.
And then you
Factor it more.
x squared plus 4 times x plus 2 minus x, x plus 2 times x minus 2.
Okay, and that's as far as we can go over the reals. But we're not Calc 1 students, we're your Math 415 students. So let's assume now we're in the complex numbers, Isabel, now factor it more.
So x plus 2i times x minus 2i.
Yep. So that's what we're essentially doing here. We're taking our real polynomial, we're factoring it into linear terms, which we know over the complex numbers is always possible. And what I'm going to choose to do is I'm listing out here, we're going to let beta sub I be all the real roots of f of x. And we're going to let the gammas correspond to the complex roots, the non-real roots. By what was on this board earlier before I erased it, we know if we happen to have a complex root, the complex conjugate of that root will necessarily also be a root. So we can kind of take all the complex roots of our f of x and put them in pairs. So over here, Isabel, why'd you give them to me this order? You did it the wrong way. You're supposed to do the real ones first. Also gave me the plus version before the minus. Completely butchered that. Here, we're going to say that our gamma 1, for instance, would just be 2i, and that's it. And we just have a single gamma 1 bar is negative 2i. Over here, we have beta sub 1 is negative 2, beta sub 2 would be positive 2, corresponding to the real number roots of our polynomial. And from the fact that f of x doesn't have to necessarily be a monic polynomial, meaning its leading coefficient isn't necessarily 1, it's going to be whatever a sub n this is, we'll have an a sub n out here. Everyone on board so far? Lydia, are you on board so far? What's that? Parker's distracting you with all of his swiveling? Of course. Alright, so where do we go from here? Well, I'm going to do some multiplying. I'm going to leave all the real terms alone. Question?
Yeah, I'm thinking about what parts of this we have learned.
What parts of this we have learned?
Well, we know it exists. The question is how much calculation. But
Well, depending on the polynomial, it might be very hard to actually
Yeah.
find what these factors are. Especially if, like, your a sub I are non-integers, for instance, which could very well be the case. They don't even have to be rational.
oh dear.
So, in practice, actually factoring something can be quite challenging. I mean, I tried to give Isabel an easy one, and she still managed to list all the factors in the order I didn't want them. But she got them all. But of course, there's lots of polynomials out there that are much harder to factor than that.
She did it great. She did it in the exact reverse order.
No,
No.
well,
Almost.
almost. I wanted this one third, this one fourth. Yeah, no, actually. If she had done the exact reverse order, I would have been happy. All right, let's actually do this. A sub n times x minus beta sub 1, x minus beta sub k. One thing I will note These do not have to occur in pairs like these do. Technically, if beta 1 is a root, the complex conjugate of beta 1 should also be a root. But that's just beta sub 1 again, so you don't actually have to repeat anything. And what I'm going to do, I'm going to multiply all these together in pairs. So if we multiply this first pair together, we'll get x squared minus, what? Gamma sub 1 plus gamma sub 1 bar x plus gamma sub 1 times gamma sub 1 bar times dot 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 times x squared minus gamma sub s plus gamma sub s bar x plus gamma sub s bar. So here we're just kind of foiling together these terms, each pair of complex linear terms. And here's something that's fun. I've got a question for you. If I was to take something of the form a plus bi and add it to its complex conjugate, what kind of result are we going to get? Lincoln?
2a.
It's going to be a plus bi plus a minus bi. It's going to be 2a. Hey, what do you know? That's a real number. If we were to take a plus bi and multiply it by its complex conjugate.
You did that twice. You just made that the non-complex.
Now it's not the complex.
That's true.
Oh, so I did. Say, what did I, this is not the same. I thought you meant I did this same thing twice. Well, we're going to get a plus bi, a minus bi. What does that simplify to? Emily Rose?
A squared minus b squared.
Incorrect. A squared minus b squared times I squared. But what's I squared?
A squared plus b squared.
Technically comes out to like a squared minus negative b squared, so it's a squared plus b squared. Which is also a real number. So this is a factorization where each of these factors is a real number. Or is a real polynomial, I should say. So this whole thing, in other words, up through this whole thing, all elements of real polynomials. For instance, going back to Isabel's example, when we multiplied the x, if we multiplied this one pair together, we suddenly get a pair that pair multiplies together to give us a real quadratic term. So what does that tell us? It tells us every polynomial over the reals will factor over the reals into a product of linear and quadratic terms. Must factor in a polynomial ring into a product of linear and or quadratic terms. The linear terms, just coming from the real roots, correspond to the real roots of your polynomial. The quadratic terms, at least the irreducible quadratic terms, over the reals, correspond to the complex roots, the imaginary roots of your polynomial. All right, Isaac. Now we're going to use the assumption, or no, it was Jonah, wasn't it? Who's getting on me about, like, are we assuming f of x is irreducible?
That was Jonas.
That was Jonah, okay.
Oh, I concur.
All right, Jonah, now we're going to make the assumption that f of x, our original, was irreducible. So if every polynomial factors into a product of linear and quadratic terms, and if we have something that's irreducible, what can we necessarily say about it?
That mean that it can't factor further, so it has to be linear. It has to be linear or quadratic.
Yeah, it has to have a factorization like this, and it can't have more than one of these terms, other than the a sub n, which doesn't count. Thus, it has to be a single linear or a single quadratic term. So thus, if f of x in here is irreducible, it must consist of exactly one linear or quadratic. And there we go. That's our proof. So essentially what we're doing is we're proving something like x cubed minus 4 pi x plus e to the pi squared. That x becomes x squared x minus 7. We're showing that can't possibly be irreducible over the reals. Why? Because because we know that something like this, that's a real polynomial, has to factor into linear and quadratic terms. Since it's degree 3, it has to have at least 2 of those terms. Therefore, it's not actually irreducible, because it has to be able to factor into at least 2 non-constant terms. Yes, Lincoln.
Why, if part of this proof shows that the complex conjugate of any root must also be a root, why doesn't that show that every real root must be at least of order 2, or rather, right? So if you have a real root, that has to be a repeated root, which is obviously not actually.
Well, technically, it's like if f of, let's suppose r is some real number. So we proved that f of r equals 0 implies f of r bar equals 0 from, well, what was originally on this board before I erased it. Well, that's really just the same as saying f of r is 0 again. So the argument we made here says that if you have any complex root, you're guaranteed, if x minus gamma sub 1 is a root, x minus gamma sub 1 bar must necessarily be a root. If x minus beta 1 is a root, if beta 1 is a root, meaning x minus beta 1 is a factor, then x minus beta sub 1 must also be a factor. But we don't actually have to add anything for that second copy of x minus beta 1 to be a factor. We didn't guarantee it has to be a factor twice. We just said if 1 is a factor, this other must also be a factor. Does that make sense?
Yeah, I think so. So to just we're only adding the term for the complex conjugate because basically that is what the additional information requires.
Right. And we know from the factor theorem from last week that gamma being a root is equivalent to saying x minus gamma is a factor. So gamma bar being a root over the complex numbers means x minus gamma bar would also have to be a factor.
Wait, so with that pointed out, have we missed a step in this? Just because we've shown that if f of gamma is a root, so is gamma bar, but we haven't. But there could be multiple. we haven't shown that there couldn't be multiple roots of one of a number and not of its conjugate. Have we?
Oh, I see. I got you. You mean like, suppose gamma sub 1 is a root, couldn't we have like this be a factor only once, but this appear like as a factor of multiplicity 2?
Right.
Oh yeah, you're right. I didn't consider that.
But
It ends up not mattering because you could just take derivatives and show that like the multiple.
or you can just factor out a pair and then you're left with
Right.
the situation we were in before, because it should be
Right. Exactly. There's several ways around that. You're right. I should probably address that though. Yeah. One way is you could show by taking like an appropriate number of derivatives, for instance, that like if this factor has multiplicity n, then this factor must also have multiplicity n. If the product came out to be reals, by basically just taking the derivative and then repeating the same process we did over here to show that if gamma is a root of the derivative, then gamma bar would have to be, meaning if gamma is a double root of the original, gamma bar would be a double root, and you could repeat that process as needed. That's true. I did not actually consider this when going through the proof, but if we wanted to be precise about it, we should include something like that. Sorry, Andrew, were you gonna say something?
No, I was just gonna say like, even if that were the case, we could still arrive at this conclusion and just say like, if it's of degree greater than 3, then there will be a pair that we can pull out.
Right.
So maybe, yeah, we wouldn't get the stronger claim that you can't factor everything into linears and quadratics, but you can still claim that. Well, actually, yeah, maybe you could get there eventually. But
Yeah, you'd still have to do some more work, I think, but you would arrive there eventually. This is moral of the story is this is an issue which we do need to consider, but it ends up being one we could work around by just repeating the whole complex conjugate root thing if need be, however many times.
Are we going to factor that polynomial?
No.
We could use the cubic formula.
You know, Jonah, knock yourself out.
I was just trying to.
I will be doing other things with my life.
I was just trying to factor x to the 4th plus 16 to see if my.
Oh, plus 16?
Yeah.
Oh,
it's a lot harder.
It's x squared plus 2i, x squared plus 4i times x squared minus 4i, and then you have to take square roots of imaginary numbers. Take complex analysis if you haven't to learn how to do that.
I know how
But
to
I
do
know
that.
you know how to do that, so put it in polar form, etc., etc. It's not
It
that
just
bad.
didn't come out pretty.
It's
showing the factor in this one.
okay. Look, there's a lot I want to get to this semester, and if we go through and look at and carefully prove every single little piece, it will never end. So at some point we have to make choices. So that handles this. So that handles this thing. First thing I wanted to prove today. So what's kind of our consequence of this? Our consequence of this is honestly, finding irreducible polynomials over the reals is boring and easy. Because if irreducible requires that you're linear or quadratic, you can immediately say, okay, degree 3 or higher, boom, not irreducible. Is it linear? Boom, automatically irreducible.
Oh.
If it's quadratic, check to see if it has any roots with the quadratic formula. If it does, then it's reducible. If it doesn't, then it's irreducible. But overall, determining whether a polynomial is irreducible or not over R, thanks to this result, becomes relatively easy. Only slightly more work than doing it over the complex numbers where it's literally, is it linear or not? So that's why we're not going to be looking much at this from here on out. This is where it gets spicy and much more difficult to determine when is it actually irreducible or not. Speaking of which, let's look at Gauss's lemma. Where Gauss's lemma is going to be what I have here for number 2, that if you have an integer polynomial that is irreducible over the integers, then it must also be irreducible over the rationals. So let's say if f of x and z of x is irreducible in integer polynomials, then then f of x must also be irreducible over the rationals as well. Proving irreducible over Q implies irreducible over Z is pretty straightforward. Perhaps it'll even be a homework question at some point. But proving the backwards direction is much more challenging and much less trivial. So here we go. So it's going to be a proof by contradiction. We're going to assume that f of x does factor over Q and then show eventually after many laborious steps that something goes wrong, or that somehow we get a factorization over Z as well in that case. So let's suppose f of x is irreducible over integers, but that in Q of x over the quotient, oh excuse me, I mean rational polynomials, that we can factor f of x into a product of two polynomials of smaller degree. That we can factor f of x into some g of x times some h of x, with g of x, h of x both being rational polynomials with 1 less than or equal to the degree of g of x and the degree of h of x, but both of these being strictly less than the degree of f of x. So we're assuming this result does not hold, that you can have an integer polynomial be irreducible in the integers, but not over the rationals. So, what's the first thing we're going to do with this? Well, what relationship does the rationals have with the integers? Lincoln?
The integers are a subset of the rationals.
Yeah, I mean they're also a subset of the complex numbers, but something more specific to the rationals. Every rational number can be multiplied by an integer to get an integer, right? Which means by extension, any rational polynomial, meaning any polynomial whose coefficients are rational, can be multiplied by some integer. Take the least common multiple, for instance, of all the denominators of your coefficients. But you can multiply any rational polynomial by an integer to get an integer polynomial. So we're going to do that here and say for some natural number, or for some positive integer n, n times f of x can be written as a product of two integer polynomials. So for some positive integer n, we can write n times f of x is equal to g hat of x times some h hat of x for some g hat and h hat that are integer polynomials, with the degrees of the original g and h matching up with the degrees of g hat and h hat. So for instance, it would be like if I gave you product of, I don't know, x squared minus 4/3 x plus 1/3 times x minus 2/5. That would be a product of two polynomials. Yes, I know the product's not in is not in the integers, but that's irrelevant. I claim there is an integer we can multiply this by and write it as integer times degree 2 polynomial over the integers times degree 1 polynomial over the integers. Seamus, what integer would you multiply by?
15.
Yeah, we could just multiply this by 15, and suddenly we would get, we just split this up, multiply this piece by 3, this piece by 5, and we would get 3x squared minus 4x plus 1 times 5x minus 2. So if you have a product of two rational polynomials, there's a way to multiply by an integer to get a product of two integer polynomials. And that's what, and that's when we take a water break, because what is happening to my voice? Oh.
You realize you're on
Mildly intrusive.
Only mildly intrusive. I just kinda wanna see.
you're on film.
I just wanna see what
Yeah,
happens.
you
no, Lydia, well, Lydia's not gonna turn
yourself,
off.
dude.
Whoa, okay. Okay, let's see if I can hold out for the rest of class. Oh, thanks. Any questions or comments about what we've done thus far? Sorry, smiley face, but I need the support space. So now what we're gonna do is we're gonna assume n is the smallest element in Z plus for which this occurs. So in other words, down here, when we say we can multiply f of x by some integer n to get it in the form of integer polynomial times integer polynomial, we're assuming there's some minimal positive n for which we can do that.
Why is it in Z plus and not just the natural numbers?
Zero. Throws everything.
What is zero?
Because I don't know, because that's what I felt like doing. Would it make you feel better if I said the natural numbers?
Yes.
No.
Maybe.
I'm ignoring you. So you might be able to guess what we're ultimately hoping to show is that we can always find is that if n is the smallest, we can find something smaller that'll also get the job done, which would be a contradiction, which would mean all of this is hooey. Alright, so g hat, h hat. We're going to need formulas for both of those. We're going to let g hat be of the form a sub k x to the k plus plus a1x plus a naught. And h hat we're going to assume has the form b sub s, the bs polynomial, up through b naught. Where all of the coefficients are integers. Because they're integer polynomials.
Why K and S? I mean, just because those are like in separate parts of the alphabet, are those just commonly used?
For K and S?
Yeah.
That's what the book used. I don't know. We need to call them something.
I just often like when you're doing something with math, often it's adjacent letters.
Oh. No,
and I was wondering like what motivated that choice.
Well, we can't use A, B, F, G, or H. I like K because Kevin starts with K, and I like S because Gerstel starts with S.
But short of the L.
We don't talk about that one.
I think
I mean,
Well, no, but
Jonah.
you just do this though.
Jonah, would it make you happier if I wrote A sub degree of G and B sub degree of H?
Ooh, I like that.
That way we wouldn't have to introduce new variables, but our lives would be more miserable going
Yeah.
forward.
Use that fancy little degree notation.
Ah, yes.
Alright, I need to be this.
I hate that.
I can
All right, Isaac, answer me this. Why can't n be 1?
Well, if n were 1, then G and H were in. We're in Z. Z is then X to begin with. And that would cause a problem with the.
With that, right?
Yes.
Yeah. Yeah, we know n isn't 1 because then we just get g hat and h hat or g and h, but that would give us a factorization of of the original f of x over the integers, which can't happen. So as else, g prime equals g, and h prime equals h.
H hat,
Oops, sorry.
don't make
The
more
book,
of them.
sorry, the book used g prime and h prime, and I thought that was stupid because it made me think of derivatives. So, but I was looking at the book this morning before class, so if I accidentally do that again, just let me know. Giving a contradiction. So n is at least 2. What does that mean? It means n has to have a prime factor. We're going to let p be some prime factor of n. Here's what I claim. I claim p is going to divide every single one of these coefficients. Or p has to divide every single one of these coefficients. Pretend I've underlined a whole bunch more potentially in between here and here. Meaning p has to either divide all the coefficients in h hat or all the coefficients in g hat. And that's going to ultimately lead to a contradiction down the line. So let's prove that one. Prove that claim with a better piece of chalk. It has to divide all the coefficients in 1. Yes, I'm doing a proof within a proof. The textbook has this as a lemma within the proof, but I'm like, I feel like in order to make a lemma, it has to be incredibly contrived what you're assuming, so I just figured in a proof. So we're going to suppose, again, we're going to do a proof by contradiction here. So we're going to suppose not. I.e. for some fixed I less than or equal to k, and some fixed j less than or equal to s, we have that p divides a naught, a1, up through a sub I minus 1, but p does not divide a sub I, and p divides b naught, b1, up through b sub j minus 1, but p does not divide b sub j. So in other words, we're saying if p doesn't divide all of these coefficients, pick the first coefficient going from right to left that it doesn't divide and call that a sub I, and pick the first coefficient going from right to left that p doesn't divide and call that b sub j. Sound good? All right. Let's see who knows. Let's see who knows how to do long multiplication of polynomials. What's the coefficient on x to the I plus j in n times f, which is equal to g hat times h hat. So in other words, suppose we were to take this polynomial, multiply them together, we're going to get a hot mess. But what would we get? But we're going to get another polynomial. What would be the I plus j coefficient of that polynomial?
It'd be a sum of a whole bunch of terms.
It's going to be a sum of a whole bunch of terms, depending on the degree of g hat and degree of h hat, and how big I and j are. Turns out the sum we're going to get is a naught times b sub I plus j plus a1 times b sub I plus j minus 1 plus a sub I b sub j plus a sub I plus j minus 1 b sub 1 plus a sub I plus j b naught. But here's the thing. We know p divides all these terms because p divides a naught, a1, a2 up through a sub I minus 1. Because p divides b naught up through b sub j minus 1, p is going to divide all of these terms. As p divides a naught, a1 up through a sub minus 1. As p divides b naught, b1, b sub j minus 1. This part seems fairly contrived?
Yeah.
So do you. This is why I didn't ask the backwards direction of this thing for the homework question.
Yeah, that's pretty visible.
So, well, we know so since p divides all of that, what does that mean?
The only one it doesn't divide is AI, BJ.
Yeah, that's the only one it can't divide. But that would imply the whole sum would be not divisible by p, because thing not divisible by p plus a bunch of stuff that is divisible by p necessarily isn't divisible by p. But this whole sum is going to be a coefficient that's a term in n times f, and n is a multiple of p, so all of the terms in g hat times h hat, all the coefficients should be multiples of n, hence a multiple of p. So we would have a contradiction there. Let's write some of that down. Thus, only a sub I b sub j is not divisible by p in this sum. So the whole sum is divisible by p. Hence, the I plus j, the x to the I plus j term in n times f, which is equal to p hat q hat, is divisible by p.
Where did P hat and Q hat come from?
P, so remember we had originally supposed that we had our f equal to some p times q, where these were both rational polynomials, but f was an integer polynomial.
Weren't those just
G and H.
I don't remember.
Oh, those were G and H. Where did I get P and Q
You
from?
also wouldn't want to double your P's like that.
G hat and H hat. That's what I meant to say. Look, there's a lot of letters floating around here. I'm getting mixed up. Yeah. Yeah, no, this is, yeah. F is originally in the form G times H, where D's are rational.
Yeah.
Then we multiply
That's
by
fine.
N
That's
and G
fine.
hat and H hat. And that's what I meant. Yeah, like I said over there. Look, my voice is going, man. It's hard. But this is a contradiction because N is a multiple of P. So P divides this, which means P divides this, which means P should divide all the terms in that. And that's not the case. As all terms N in F equals, oh my gosh, I almost did it again. G hat, H hat are integers. Hence must all be divisible by M, hence P. Whew, that was a lot. And we're not done yet. We just proved this claim.
Wait. Oh, okay. Never mind, I figured it out.
We good? Neato burrito. So all of this was just to prove this claim, that P either has to divide all the coefficients in G hat or all the coefficients in H hat, not P hat and Q hat. I don't know where I got those from. I mean, I like Zelda games, so P hat is a Zelda hit in me, but that's not relevant to the conversation.
But did we say that N was a multiple of P?
Yeah, well, we defined P to be, let P be some prime factor of N, was how we defined P.
Yes.
I'll erase now. Sorry. If only someone didn't have to take the class remotely, we could use some sideboards to keep some of this.
Or if you could just let me move the camera.
Shut up. Alright, so we've proven our claim. So we know P has to divide all the A sub I or all the B sub I. So we're just gonna, without loss of generality, say it divides all the A sub I.
If you put like a fisheye lens in front of the camera.
Say what?
If you put a lens in front of the camera so that
Oh, you could really good too. Or you could
Lydia, they want you to not be able to make out anything. I'm helping you.
or you could let me control it. By
I want to finish this proof today, okay? Let's keep going. So P divides all coefficients in G hat. So the A sub I. If not, just swap what you're calling G hat and what you're calling H hat. So what does that mean? Well, that means that G hat is a P. I'm going to start that sentence over. That means P divides all of G hat, meaning G hat is going to be P times some other polynomial, G double hat. That's right, we're bringing in the double hats.
This is getting spicy.
Don't worry, it's not much more to go. Say what? Do you see how much it was snowing earlier? Sometimes two hats are called for.
Yeah, and then it just stopped.
I know, it was fun. We were talking about contingencies, statements that are sometimes true, sometimes false in my 8 o'clock Math 105. And I said, it is snowing outside as an example of a contingency. That is false at the moment, but could be true at other times. And then by my 9:30 class, I was able to do the same example and say it's very much true at the moment. But anyways, so P divides all the coefficients in G hat, which means P divides G hat, which means G hat has to be some multiple of P times some other polynomial. Then, since NF equals G hat times H hat, we can write N over P times F is going to be 1 over P times G hat h hat. Keeping in mind n over p is an integer because we assume p divides n, which is equal to 1 over p times pg double hat h hat, which equals g double hat h hat. What do we know about g double hat? Well, we just said that's an integer polynomial. We know this is an integer polynomial. And we have contradicted something. What if we contradicted? Specifically with regards to n and how n was defined.
He said it was the smallest.
Yeah, we said n was the smallest integer, smallest positive integer for which n times f could be written as the product of two integer polynomials, and yet we have just found n divided by p, for which that's the case. Let's go back over here. But this contradicts. N is the smallest element in the integer polynomials for which n times f could be written as a product of two integer polynomials. Whew. So, we have a contradiction, finally. What exactly have we contradicted? Well, we contradicted our original assumption about f of x, which is that f of x is irreducible over z, but not q. As f of x can't be irreducible in the integers, but not in rationals. I.e., irreducible over the integers implies irreducible over the rationals. Wha-bam.
As the prophecy has foretold.
As the prophecy has foretold. I seriously considered giving you this as a homework problem.
We're all very grateful that you didn't.
I lied, I wouldn't have given you that as a homework problem, it's all in the book. So I'm not going to give you a homework problem that's just literally copy what the book said. Except for the part where the book, instead of using g hat and h hat and g double hat, it had prime. So like instead of g hat and g double hat, it had g prime and g double prime. And I couldn't shake the mysterious feeling that like somewhere somehow derivatives are being taken. Which are bad because we need the degree to be preserved. We need the degree of g hat, and the degree of g double hat to all be the same. And if derivatives are being taken, that certainly isn't happening. Unless they're all like constants, zeros, but that would break other things. All right. Well, bam, we finished this packet. We'll clap that. I don't know why. So, all of this was just to prove irreducible over z if and only if irreducible over q. Which is nice. That means that in order to answer questions about polynomials being irreducible over q, assuming they're integer polynomials to begin with, we can just check to see are they irreducible over the integers instead. And if they're irreducible over the integers, well then that gives us irreducible over the rationals. Obviously, if I'm giving you some polynomial with rational non-integer coefficients, that's not even going to be in z of x, so we can't just check that multiply by some integer, you'll get an integer polynomial.
Yeah.
And that is going to be a very relevant technique for us for checking those sorts of cases. All right, y'all heard of Einstein? Albert? Kind of a big name in physics. Matthew, does that sound vaguely familiar to you?
I thought you said Feinstein. I'm like,
Weinstein! No, I'm not. No,
Your
I don't know the proper German pronunciation. I defer to Dr. Volosov on that one. Einstein.
Would be like shine.
Einstein. How about Eisenstein? His next theorem is Eisenstein's criteria.
Is that why you
Is
brought
it
up
doing it in the
Einstein?
next 3 minutes?
Let's do it.
Let's do it.
We can do it.
Yes.
Heck yes.
We're not going to prove it in the next 3 minutes, but we can at least look at it.
That's chicken right there.
It's not as long as this proof was, but it's not a 3-minute long proof either. I'll let you use your packet. So Eisenstein's criteria is kind of a fun test you can do to check whether a polynomial is irreducible or not over the integers. Just, if you have something, like for instance, where's my eraser?
Hey man, we got like 2 minutes before 5 cents. I gotta have it yawn.
Okay. Alright, let's say we want to prove this thing. Is irreducible over the integers.
So
Zoinks! Jinkies. I mean, you could use the fact that it's degree 3 to say this thing is irreducible if and only if it doesn't have any roots. Which is the case. Then you could use like the rational roots test to check if this thing has roots. Or you could use Eisenstein's criteria, which is to say, notice how 3 divides 21. 3 does not divide 49, so I meant to say 7. 7 divides 49. 7 divides negative 14. 7 does not divide 8. 7 squared does not divide negative 14. Boom, irreducible. And that is Eisenstein's criterion. Where if you have some integer polynomial, and you can find some prime number that doesn't divide your leading coefficient, so 7 doesn't divide 8, 7 does divide all your other coefficients, and your prime squared doesn't divide the last coefficient. This is a multiple of p, but not p squared. Then the polynomial is guaranteed to be irreducible.
Oh. But this is not true of all irreducible polynomials, right? Or is it?
You tell me.
Oh. That's what I'm voting.
I guess
Well, let me ask you this.
you could just x squared plus 1.
Let me ask you this. Is that an irreducible polynomial over the integers? Is there any prime that doesn't divide 1 but that does divide 4? 2, right? Does 2 squared divide 4?
Yes.
Oh, bummer. So no. You can have irreducible polynomials for which no prime satisfies these criteria. But if you do have an irreducible polynomial where these criteria are satisfied, then it is guaranteed to be irreducible.
Did you mean x squared plus 4?
Oh, yeah.
What to say?
Yeah, because you're asking me irreducible. I don't know, I was just trying. Yeah, you're right. Alright, that's Parker in the video. Alright, so when we come back next time will be much less scary theorem based and much more, let's play around with a bunch of examples and see what sorts of tricks we can use up our sleeves. We are going to prove this theorem, by the way. We are going to prove Eisenstein's criterion. But then the rest of the packet, and Eisenstein's criteria is not that hard to prove. The rest of the packet is going to be looking at a bunch of examples and doing a bunch of tricks.
Pizza.
And then homework 4 is going to be looking at a lot of examples and doing a bunch of tricks. Have a good one.